Welcome to EEMS 265. This video provides a brief overview of the graphical features to set up and configure the EFDC Plus SEDSL-J sediment transport model. SEDSL-J stands for Sediment Dynamics Algorithms as developed by Ziegler, Lix, and Jones. Let's get started. The initial subroutines for the SEDSL-J sediment transport algorithm were developed by researchers at Sandia National Laboratories. The subroutines have been updated more recently by DSI for use in EFDC+. The primary purpose of the SEDSL-J approach is to improve the treatment of complex mixtures of different size sediment particles, which are more typical of natural conditions. A unified treatment for multiple sediment classes supports prediction of changes in the water column, sediment bed properties, as well as the flux of materials across the sediment-water interface, based on the predicted flow field. Another advantage of the SEDSL-J approach is that it can employ site-specific erosion rate data obtained from SEDFlume core tests, which measure the thickness change of sediment bed as a function of bed depth and applied shear stress in a controlled flume experiment. A detailed description of SEDFlume analysis is available in Jones and Lix 2001. Users can activate the SEDSL-J sediment transport module by clicking on the SEDSL-J sediments checkbox in the EFDC modules form. Then, the sediment branch will appear under the modules tree in the model control form. Right-clicking on the sediment branch will open the SEDSL-J sediment and sediment bed properties dialog. Under Major Settings, users may specify the number of sediment bed layers and the number of sediment classes. In the General tab, users can determine primary computational options for the SEDSL-J submodel, such as allowing bed morphology changes with hydrodynamic feedback, accounting for bed slope changes in the erosion rate calculations, and applying anti-diffusion to vertical sediment concentrations. The date and time to start sediment transport field allows the user to specify the Julian date to begin computing sediment transport processes. This feature is primarily used to allow for a spin-up period in the simulation. The deposition limit of water column sediments field requires a value between 0 and 1. This parameter represents the minimum fraction of sediment in the bottom water column layer allowed to deposit in a single time step. The maximum deposition layer thickness determines the maximum thickness limitation for sediment bed layers that receive deposited sediments during simulation. The minimum water depth for shear stress updates field specifies the minimum water depth where shear stress is computed. The sediment time step field specifies the frequency of sediment transport process computations during the simulation. The erosion rate options frame provides 3 options for erosion rate matrix data type. Each option requires different types of erosion rate information. Users should review the EFDC Explorer knowledge base pages for further details on these options. The temporally varying erosion rate parameters provides an alternative option allowing users to set up an erosion rate matrix from an external ASCII or binary format file. The hard bottom option allows the users to specify in which cells erosion or deposition processes are allowed to occur. For example, no interaction between the sediment bed and water column can occur at deactivated cells where a 0 value is assigned. Under this condition, all sediments remain in suspension until they reach an active bed area. Next, we will take a look at the Sediment Properties tab. Under Sediment Class Properties, the user can set the representative particle size, critical shear stresses for erosion and suspension, and settling velocity for each sediment class. These transport parameters determine the behavior of the sediments in active motion. The Sediment Info button reports the critical shear stresses and settling velocities computed based on the particle sizes entered in the sediment class properties table. The critical shear stresses and settling velocities are calculated using Van Ryn's equations, and these resulting values are provided in the pop-up window. However, these values will not be used in the model and are only provided as a reference guide for reasonable values based on theory. If users click the Initialize Defaults button, the critical shear stresses and settling velocities in the sediment class properties table will be automatically filled using the values computed with Van Ryn's equations. Next, we will take a look at the Sediment Bed tab. In this tab, users can specify the sediment properties for the active and deposition sediment bed layers, including the active layer thickness multiplier, number of sediment size categories, and bed load options. For erosion rate option 1, the number of shear stress categories to calculate erosion rates can be specified. In the Sediment Erosion Characteristics table, the user can specify the lookup table to determine the critical shear stress for active and deposited layers as a function of their D50 size. Bed load options allow the user to activate bed load computations for coarser classes and set the cutoff grain size for the bed load computation. Next, we will explore the Erosion Rates tab. Here, the user can specify the active and deposited sediment erosion matrix, which is the lookup table that determines the erosion properties for active and deposition bed layers as a function of their D50 size. The matrix format displayed in this frame varies depending on the erosion rate options selected in the General tab. For more details about the erosion rate options available, please see the EEMS knowledge base page under the links below. The next tab is for core definitions. Here, users can enter several erosion rate datasets acquired from SED-Flume core tests, which will be used to define spatially varying erosion properties of the parent bed layers. The user can set the number of SED-Flume cores and then assign the key measurements for erosion rate properties associated with each core. For example, if the number of SED-Flume cores is set to 3, the drop-down menu will be populated with 3 cores in the Sediment Bed Characteristics frame, where the name of each core can also be modified by the user. In the Bed Layer Properties and Grain Size Distribution frame, the user should enter the critical shear stress, dry bulk density, layer thickness, and grain size fractions measured from each vertical layer of each SED-Flume core. The matrix for SED-Flume measured erosion rates can have different formats depending on the erosion rate option selected in the General tab. General descriptions of each option are available in the documentation for erosion rate options 1, 2, and 3. The Core Assignments tab helps assign SED-Flume core definitions for physical and erosion properties to model grid cells. This process defines the horizontal distribution of SED-Flume properties over the model domain. When multiple SED-Flume cores have been defined, users can set core assignments on a cell-by-cell basis using the Allow Core Definitions on a Cell-by-Cell Basis checkbox. Users can set the default core number based on the index value of the core's input in the Core Assignment tab. The default core will be assigned for areas of the domain where no SED-Flume core has been assigned. With the Using Nearest Neighbor approach option, SED-Flume core definitions will be allocated to the cells based on their locations as provided in the Core Assignments tab. When using the Assign Core Numbers using Polygons with IDs option, the user can assign SED-Flume core definitions to the cells within the area specified as polygons using a compatible shapefile or text format. When the Assign Cores using Polygon IDs option is selected, the user must specify a path to the shapefile containing the polygons and ID values to be assigned. EFDC Explorer can generate the core assignment input files following either the DSI or Sandia Labs format, depending on the version of EFTC being used for the simulation. The SEDSL-J wave options can be set by the user to impact bed shear. The wind wave options dropdown provides 3 options: no wave action, wind wave SEDSL-J, and ST wave. While these options can use the EFTC Plus internal wind waves, at this stage they will only impact the boundary layer. If the standard SEDSL-J wind option is selected, then EE wind wave option is not used. In this case, the user must ensure that they have all the correct files, such as fetch.imp. If the ST wave option is selected, then correctly formatted ST wave files are required. In the Miscellaneous tab, users can set the skin friction options and select to use constant bed shear stress or not. The user should refer to the SEDSL-J user manual for more information on skin friction options and the use constant bed shear stress options. Under the class maximum grain size frame, users can set the maximum grain size for each sediment class that are used in the model. However, the user-defined maximum grain sizes are used only for computing median grain size, and the SEDSL-J model simulates transport using the representative particle size of each class. Thank you for watching. You can find the link to the next video below.